So today, let's talk tornadoes. First of all, you know what a tornado is. You've seen them, you can visualize a tornado, but we need a good working definition of what a tornado is. And you know my penchant, I like definitions that make sense. They're simple. They describe what we know a tornado to be. So, in that mindset, let's define a tornado. It is a vertical. That's important. We know tornadoes are going up and down. It is a rotating column of air. That we also know to be true, but specifically it is attached to a cumulonimbus cloud. So this is a good definition that's going to kind of cover any situation in which we need to decide, is that a tornado or not? Well, let's think about this. A dust devil. We kind of used the moniker of a dirty tornado when we described this in the previous unit, but a dust devil does not fit the definition. It is a rotating column of air. The difference is it is not attached to a cumulonimbus cloud. So how do these tornadoes form? And this is a tricky discussion because tornadoes still aren't completely understood by scientists. They're very hard to study and get good data on. But we know there are some conditions that have to be true in order for a tornado to form. The first we're going to look at, this is kind of a generalization. We know that the winds going across the ground are weaker than the winds the higher up you go, because down here near the ground, there's a bunch of stuff. We get a lot of friction from trees and buildings and topography. So we can't help this but happen where these winds up here blow a little bit stronger than the same winds down here. Well, that means they kind of overlap one another and they make kind of a spinning vortex. This happens all the time. That by itself is not a tornado. However, if we come across a situation where we get a rising cumulus cloud, the ground is extra hot, and the air and the moisture with the air is forced to go up. Well, now my spinning vortex of air can kind of get lifted up on one end versus the other. Over here, maybe it's not so hot and the air isn't rising, but right here it is. So it's going to take my spinning vortex and try to turn it up vertically. The colder it is up here versus the warmer it is down here, the more likely that is to happen. And the more likely you're going to get the stronger updraft that is going to pull that vortex vertical. So eventually you get a situation like this, and now we've got that rising cumulus cloud, which acts like a vacuum cleaner, and it's just pulling air up. A final ingredient that's also important is what we call wind shear. We need something up here where the winds have a dramatic change in direction. And what that does, it gets that vortex spinning extra fast, which allows it then to suck up more air and turn into what we know to be a tornado. So some key ingredients. You got to have some moisture because we got to get the clouds. We got to have some colder air up high to make that water condense, make the clouds, and create the updrafts. We got to have one of those lifting mechanisms, convection, converge. You got to have one of those things that makes the air rise. And finally, we got to have some kind of wind shear that's going to get my vortex, my spinning column of air, to spin faster to the speeds where now we got a tornado. So those conditions tend to happen here. We get some warm and cold air that's along a front, and it happens most violently along those occluded fronts. You got to have something making the air go up, and you got to have the moisture to make clouds. So where are all those things most likely to happen? In supercell thunderstorms. When are these conditions most likely to occur? Well, if we think about USA tornadoes in the USA, and we look at it over the course of the year, we notice it seems to be May, June, July, we see April, seems to be mostly in the late spring and early summer. That is generally the case because that's when you have the most violent mixing of the cold and the warm air. And that's just over the whole United States, just the average over the United States. But we know that the temperatures fluctuate at different times for different parts of the country based on their latitude. So let's look at Georgia. For Georgia, however, our tornado months are March and April. By the time we get over here, we're too hot. We don't have as much cold air anymore, so we're not as likely to have the cold air that it precipitates the formation of tornadoes. So for Georgia, our tornado season is a little bit earlier than the U.S. average. So what time of day? Well, if we look at the graphic, it seems like tornadoes seem to form in the late afternoon, early evening, because tornadoes are associated with severe thunderstorms. And we know severe thunderstorms are more likely to occur late in the afternoon to early in the evening. Now, where do tornadoes form in the world? We're going to concentrate mostly on the United States, but in the world, tornadoes can form on any continent except Antarctica. I think you get why they can't form on Antarctica. There's just no hot to mix with the cold to make our thunderstorms. Ironically, the United States has more tornadoes than the entire rest of the world combined. We are tornado central, and we're going to explain why. Remember the key ingredients. I have that warm and cold air. It's got to have the moisture. Got to have just the right ingredients to make a tornado happen. If we look at the United States, the way our geography is set up, first of all, we've got these Rocky Mountains out here in the west, and it really acts as a guide for that jet stream to pull that cold air down from Canada. We also have this nice extra warm bucket of water down there called the Gulf of Mexico. We talked about how warm the Gulf gets, and that provides us a very consistent and strong supply of warmer, moist air. Well, those two meet, and where they meet? In the Great Plains. The Great Plains is flat. There's not a lot to get in the way of the wind, so you can get those strong vortexes of winds that can then be turned vertical and make tornadoes. So we have all the key ingredients to make tornadoes happen, and they do. Let's look at someplace else. Well, the Mediterranean. In Europe, it's pretty warm, nice, warm, moist air. Great. Here we've got some cold air coming down from northern Europe and Russia. Great. And if they meet, we can get a tornado. But in the middle of Europe, the mountains are oriented like this. So the Alps acts as a barrier to keep those two air masses from meeting. So consequently, they got only part of the ingredients, but they're not allowed to mix to make tornadoes. In the United States, where do we get them more often? And that once again is going to follow the same pattern with tornado or thunderstorms. We get tornadoes happen more in the Midwest because that's where you tend to get the supercell thunderstorms. You'll notice not many in the West. Here's a image of tornado tracks. Notice once again, not much in the West. Why don't they get many tornadoes in the West? There's two reasons. One, they got a lot of mountains that get in the way of that airflow. It's hard to get that spinning vortex of air that you then can't then turn upright. Second reason, they're missing the moisture to make the clouds. Now, what states have very few tornadoes? You notice the continental United States in the west. More specifically, let's look at Alaska. It says 0 average annual number of tornadoes. Why no tornadoes in Alaska? Because Alaska's just too cold. They don't tend to get enough of that warm air that's going to make supercell thunderstorms and tornadoes. So what state is Tornado King? Who are we going to say wears the crown of having the most tornadoes? Well, Texas certainly has the actual highest number of tornadoes, has 155, I guess, in this particular year. So that seems okay. Let's crown Texas Tornado King. Well, it's not fair because Texas is also a really big state. So it's not really fair to compare Texas and its land area to Oklahoma, which is smaller. So let's look at a better metric. Let's talk about tornadoes per 10,000 square miles of area. It's like the average tornado per mile, if you want to think about it that way. And in this case, you're going to see the state of Florida has the most tornadoes, but this is also kind of misleading because in Florida, most of the tornadoes are what we call waterspouts. They're tornadoes that form over water, and technically, they fit the definition of a tornado. Is it a rotating column of air attached to a cumulonimbus cloud? Answer is yes. But waterspouts tend to be much weaker than the ones that form over land. So yes, even though technically they are tornadoes, we've got to take that stat with a grain of salt. So what state has the most tornadoes? It appears to be Florida, but we want to throw Florida out because now we know that most of them are waterspouts and don't really count as true tornadoes. So for the purpose of our discussion, we're going to go with Oklahoma. We're going to say Oklahoma is the #1 tornado state. And if we go back to that average, you'll notice that yes, it has the highest occurrence of tornadoes per 10,000 miles, or high. Think about it as the highest amount of tornadoes per mile. That is Oklahoma. Tornado Alley is an area in the middle part of the United States where tornadoes are a lot more common and subsequently a lot more damaging. And once again, this follows our pattern with thunderstorms. That's where we get more supercell thunderstorms, especially, so you're going to have more tornadoes. And you can see it once again on this map. These are all the tracks or the lines that tornadoes follow, and you see in the middle part of the United States seems to get the most tornadoes. Look at this area right here. Seems to be kind of an empty spot where tornadoes don't seem to occur. If you know anything about geography, and you should realize that's the Appalachian Mountains, West Virginia, parts of Virginia. They don't get many tornadoes because the mountains get in the way of the tornadoes forming. Now, this idea of Tornado Alley, very well documented, but we're seeing a shift, and it's one of the key pieces of data that we're using to justify or explain weather events with climate change. We're seeing more and more tornadoes ending up over here than in what we call the traditional tornado alley. It's actually given a name. It's called Dixie Alley. Dixie meaning the South. So this area in the Southeast, Georgia included, is now kind of lumped into this category of what we call Dixie Alley. It's an area where tornadoes are becoming more and more common in the South, whereas they used to be traditionally way more common in the Midwest. So let's talk about how do we measure these tornadoes. Not all tornadoes are the same, because not all thunderstorms are the same. So we can do this. We can go outside with a anemometer and we can record the wind speed of the tornado, whether it's a static one on a pole somewhere or it's something that somebody is holding. Here's a problem. Do you want to be the guy out there holding the anemometer in the thunderstorm to measure the tornado? The answer is no. And this is one of the first problems with studying tornadoes. It's difficult to know or get enough data for a couple reasons. First of all, tornadoes, we really don't know when and where one is going to happen. They pop up when these thunderstorms pop up. And just because you get a thunderstorm doesn't mean you're going to have a tornado. They're also not very big and they don't last very long. So even if we know a tornado is happening, we don't have the time to go out there and take its wind speed and study it and see how it got started, because we don't see it until after it was developed, and by the time we get there, it's done. Finally, tornadoes are really dangerous to work with. You don't want to be the guy out there with an anemometer. So unless a tornado runs directly over a static weather station, and provided it doesn't destroy it, it's very hard to get actual direct measurements of the inside of a tornado. The old movie Twister and its remake, this is what they were trying to do. They were trying to release some wireless probes into a tornado that would send back data from inside the tornado, because once again, it's very difficult for us to get data on a tornado. We do rate tornadoes though. We describe them with the Fujita scale. This is a system that rates the strength and the severity of a tornado based on how much damage they cause. Now, this is always done after a tornado. Remember, nobody's out there measuring the wind speed of the tornado. What happens is a tornado occurs and you go out after the fact and you look around and see what was damaged. And that's how you get the rating, or that's how you tell the difference between a strong tornado and a weak tornado. It is basically a scale of 0 to 5, not 1 to 5. An F0. F stands for Fujita, F0. This is any tornado with winds less than 73 miles an hour. It doesn't really do a whole lot of damage, and about 40% of all tornadoes fall into this category. This is what an F0 tornado would do. Doesn't look very destructive, because it's not. We see up here, there are the tops of some trees, especially pine trees, get snapped off. Looks like here on the front of this building, looks like some of the siding came off. Over here, looks like we might be missing a shingle or two. But for the most part, F0 tornadoes, even though they are tornadoes, the wind speeds aren't powerful enough to really cause any damage. So we'll jump up to an F1. Winds are stronger, and these stronger winds can do more damage. You can start to take some of the surface off a roof. If you live in a mobile home, it can get moved around because it's not tied to the ground. And if a car is moving down the road, an F1 tornado can be strong enough to pull it or push it off the road. About 36% of all tornadoes fall into the F1 category. Here's an example. There's a barn. Now, this barn wasn't destroyed, but you notice some of the surface of the roof came off, some of the shingles or the covering on the roof itself. It didn't destroy the structure, it just peeled off a little bit of the roof. But if you live in a mobile homes are on wheels. They're not tied to the ground. Mobile homes can get turned over on their side or moved off of their foundation. This is only an F1. Now, a big conclusion here is that 39% are all F0s and 36% are all F1s. That means 75% of all tornadoes are F0s or F1s, meaning 75% of all tornadoes are small. We have this idea that when there's a tornado, it's a big, huge, damaging, kind of destructive event. That's not the case. Most tornadoes fall into these weaker categories. Are they still dangerous? Yes, but they're not the big, huge ones like you see in movies. Let's jump up to an F2. Winds are stronger. Now we start to get some a little more serious damage. The roof can come off a house. Mobile homes are just destroyed, and you start getting light objects being thrown around the air with such force that if they hit you, they could kill you. Only about 19% of all tornadoes fall into this category. Here's what an F2 tornado damage would look like. Here's a well-built house. And let's look and examine what we see. First of all, the top's coming off the trees, and a good portion of my roof has been destroyed. This is not the covering off the roof. The actual structure of the roof has come off. Now, this house is not a total loss. It wasn't destroyed. If you were inside that house, you survived because the walls are still intact around you. You might be scared out of your mind when the roof comes off the house, but you weren't likely killed in your home in an F2 tornado. However, this is a mobile home after an F2. And you'll notice there's nothing left to it. Mobile homes are not built very, very strong. They're very lightweight because they're meant to be mobile. And an F2 would just entirely flatten an F2 tornado. So if you live in a mobile home, tornadoes are bad news to you, even some of these weaker ones. Here's where F2s do most of their damage, and that is the fact that they can knock over large trees. Especially if the tree's weak, we're having a drought, the roots aren't set very well. These large trees can get pushed over, and if they land in your car, they'll crush your car, kill you. People have died that way. If it falls into your house, the weight of that tree could very definitely crush part of your house and kill you inside of the house. Now in F3, even stronger winds, and now we get the roof comes off the house and some walls are gone. Cars are picked up and actually moved from one place to another. About 5% of all tornadoes fall in this category. Here's what F3 looks like. If we look at the structure back here, entire roof is gone. Some of the walls are now missing. That means this was an F3 tornado. This car obviously was picked up and moved there from the parking lot by the tornado. It takes an F3 to be strong enough to make that happen. And this is how tornadoes are rated. You go out after the fact and you look at the tornado and the damage and say, okay, that car was picked up and moved. This had to be at least an F3. Now, F4s, now we're starting to get nasty. In an F4, well-constructed houses are entirely level, like the mobile home was with the F2. Cars and other large objects can be thrown through the air, not just moved, but actually picked up and thrown into other objects like your house. Luckily, only about 1% of all tornadoes get this big. This is what an F4 looks like. Here's what's left of the house. You'll notice there are absolutely no walls left standing. If you came out after this tornado and you look at this and say, okay, this had to be an F4 because there are no walls left standing. In this picture here, this was near Kansas City. Tornado came through and they're trying to assess how strong was this tornado. Well, they looked over here. Well, no walls left standing, probably an F4. And what they looked at as a piece of evidence was this boat. This boat had been picked up and thrown. The guy that owned this house here didn't own a boat. That boat came from his neighbor's house up the street. The tornado was strong enough to pick up that boat and throw it through the air into this guy's house. And that tells us it had to be an F4. Other large objects, like a big old board, what we call a 2x6 or 2x8, was picked up and thrown through the air great distances. Obviously, this is a mobile home. It wasn't anywhere near the tornado because an F4 would just demolish it. But the F4 picked up this board and was able to throw it through the air far enough that it jammed through the wall of a mobile home. That tells us this tornado must have been an F4. Now F5s, this is the top of the heap here. These are the worst, nastiest tornadoes. And in this case here, houses are not just destroyed, they are gone. Things are swept away over a wide distance. Automobile-sized missiles can go 100 yards or more. Trees have the bark come off. Luckily, less than 0.1% of all tornadoes ever get to be this big. So these F5s and even the F4s, they're fairly rare events. This is what an F5 looks like. Now this was a 2-story farmhouse. Notice there's no walls left standing. But if you look at the pile of debris back there, does that look like enough stuff to make a 2-story house? The answer is no. So where'd everything go? Not only was the house leveled, stuff that made up the house was spread over a wide area. This is a case where they find your driver's license or your wedding picture or stuff from they find it 2 counties over because an F5 is that powerful that it just shreds everything and disperses it over a very wide area. And that's what I want you to understand about the difference between F4 and an F5. There's an F4, house is leveled, but everything's right here. Your stuff is in there. You can get some of your stuff back. It's under the pile of rubble, but it's in there. If you're married and you got a photo album from your wedding, it's in that pile of stuff. Did stuff break? Sure, you're fine. China, there are things that are broken, TV's destroyed, but you can get some of your clothes back. It's in the pile of rubble. With an F5, nothing's there. It's all gone. Your wedding photo is likely shredded. Your clothes are likely shredded, torn into small pieces, and dispersed over a very large area. So the percent of all tornadoes, you can see, once again, to reiterate to you, 75% or so of all the tornadoes are what we call weak. Only 25% are what we call strong. And only 1% are the nasty, most violent ones. And we have this misperception because when we see tornadoes in movies and TV shows, it seems like they always show these. And that's not really the case. So we have this idea that tornadoes don't hit cities. And it's a very common misconception. Oh, that's something that happens out in the countryside. So why don't tornadoes hit large cities? Well, there's 2 reasons that kind of lend to this thought. One, tall buildings tend to get in the way of winds, and this is very much true. A tornado would have a hard time actually forming directly over a city because you can't get that spinning vortex to rise up very easily because the buildings are in the way. Now, the second aspect is a little skewed because if we think about our country, here's a map of cities versus country. City versus rural. By land area, our country is covered with a lot more open space. So let's say a tornado forming anywhere out here in the Midwest, there's a lot more of a chance that it's going to form over open land because the cities are actually a small part of the total land area. So it lends us this kind of thought that, okay, tornadoes don't hit large cities. That's not 100% true. Tornadoes can hit large cities. They just don't do it with the frequency that they hit rural areas.